Can you see the whiteboard? Yes. Because it's a whiteboard working. Pardon? Okay. All right. Example 3.2.1. We are doing given that it's matrix A is equal to of 2 by 2 order 3, 2 and 2, 0. To find eigenvalues, we need to form like matrix this to find eigenvalues. Find characteristic polynomial, you can say, or characteristic equation. How? Find first of all a minus lambda into I. Okay, then we'll find determinant of that and then put equal to 0 so that we can find the eigenvalues. Give me a moment, okay? Okay, so let us find it. And I will take according to A. Means we take order of I according to A. So let us find it. So A minus lambda okay, let us stop the recording of just this Zoom because we are sorry. Give me just a few seconds. Recording stopped. Okay, now I'm sharing the screen. Okay. Let us find it. So A minus lambda into I, let us find it. A we have 3, 2, 2. Okay, I think this is not support. I'm just taking a whiteboard of Zoom only. Can you see the whiteboard now of Zoom? Yes, ma'am. Okay. So, yes, lambda A is equal to 3 here, 2 and 0, and a matrix of this identity. I can give you matrix of the same order. Now let us or 3, 2 means by using scalar multiplication, we'll simplify them like this. Getting these steps and just subtract the corresponding elements of this. So lambda into I from A as 3 minus lambda, 2 minus 0 and 2 minus 0 and 0 minus lambda. This is A minus lambda. So Let us simplify 3 minus lambda, 2 and minus lambda we have. Now to find like eigenvalues, we need to find determinant of this matrix. This matrix equal to 0. Are you getting me? Values. Find determinant of a minus lambda into I and put it equal to 0 to form characteristic equation. Characteristic equation. Like take determinant of a minus lambda into I. So now find the determinant of a minus lambda, which is 3 minus determinant. Now let us simplify it and minus lambda. 3 minus lambda in lambda minus 2 into 2 and 0. Are you getting this step? Okay, now let us minus or minus 3 lambda and plus lambda 4 is equal to 0. Where 3 lambda 4 is equal to 0. And you can use a formula as well as you can solve by splitting middle term. Lambda square minus 3 lambda and okay. We solve only by quadratic formula, yes. Because we can't take splitting. Because we have this negative. So splitting middle term, this 3 lambda means yep. Yep. Square minus lambda plus and my sorry lambda and is equal to 0. Yes, middle term. Okay, so values of lambda will become minus 1 and 4. So lambda is equal to minus 1 when we take this is equal to 0 and lambda is equal to 4 0. So values of lambda are hence eigenvalues in matrix are minus 1 and 4. Got it? You got it now? Yeah, we'll do for that. Okay, we are eigen for lambda is equal to minus 1 and also for lambda is equal to 4. Let us find minus 1. First of all, we are finding to find eigenvector. Put uh, A minus I into I into X. Here this is factor, okay, is equal to 0. And this 0 right hand side we have 0 and we'll take it as null vector. Null, okay. Here we are taking matrix. So A is lambda. We need to put lambda here. So we have A minus lambda into I, 3 is minus 1 and 2 again 2 and 0 minus lambda minus. X because we have of order 2 by 2, so we can take either x1 x2 or by taking two components of vector. Okay, so let us take here x2 according to your PDF and take here zero matrix or null matrix to represent this right side. Okay, let us simplify more. So we have here 4 2 2. Okay, sorry, we'll take minus 1 we are taking, sorry. So and take x1 and x2 and null matrix on right side. You got these steps? Okay. So now let us multiply A my now multiply the smart to 0 to 5. So we'll get so 4x 2x 2. We have here minus or just a second. Okay, they are finding for lambda is equal to 4. That is why they are taking minus. Okay, okay. Sure, one by one we'll find for both. We'll find for both. This is x2. We are multiplying 2x1 plus 2. 2x1 plus x2 and we equate null matrix one by one each component. So 4x1 plus 2x2 is equal to 0. We can take 2 as a common, sorry, 2x2 is equal to 0 and 2x1 plus x2 is equal to 0 and 2x1 is equal to minus x2. Okay, so we can find eigenvector when we put any value of x. So like let's put obviously means we usually put means this value means either you can have here x1 or x2 when we find the relation between this component of vectors. Then we'll take this usually on right side 1. If we take is equal to 1, then 2 x1 is equal to like 1, or you can take x2 is equal to minus 2x1 and put x1 is equal to means we can find the relation between them by taking any number to represent this. Okay, usually we take 1. Okay, so take x1 is equal to 1, then x2 will minus 2 into 1, obviously we'll get minus 2. So required vectors we can represent as, so eigenvectors we can represent x is equal means taking 1 and minus 2 eigenvector. Okay, and let us find for lambda is equal to 4. You got it, or shall I explain you anything? Okay. So shall we do for lambda is equal to 4, or will you do yourself? What do you say? I'll do myself. Okay. So shall we do the next example? Yeah. Okay. All right. So next we have A is equal to here. We'll do directly because we have already steps to find eigenvectors and eigenvalues and only one non-zero. So first of all, we'll find it a minus lambda into I, which is equal to 0 minus lambda into take the same order identity 0 and then take this by multiplying this lambda and then subtract now. So we'll get minus lambda 1 and 0 and minus lambda. And now we need to find means we need to put determinant of a minus lambda into I is equal to 0 in value. So let us find it. So lambda minus lambda is equal to 0. Lambda into minus lambda minus 0 into 1 is equal to lambda square minus 0 is equal to 0. Obviously lambda is equal to 0. Now we so eigen, okay, which is value for the given matrix. Now let us find eigenvectors. Okay, on next page we'll do it. So to find eigenvector, put a minus lambda into I into x is equal to 0. So we have lambda is equal to 0, then we'll get obviously the same matrix as we have given into we are taking capital X having two components x1 and x2 is equal to taking null matrix. So obviously we'll have here like x2 and 0 or like 0 x1 plus x2 and 0 x1 plus 0 x2 is equal to 0. So obviously like compare, then we'll get x2 is equal to 0 since 0 x1 plus, so obviously we'll get x1 is equal to 0 because why, if 0 means this term is being 0 because of this coefficient. So when we compare with this x2, then still we'll get, then required eigenvector x is equal to having 0 0 component. Okay, one second. Okay, okay, sorry. I'm here taking eigenvector one. Okay, okay. Just a second. Okay, okay. I'm telling you just. Okay. Okay. To x1. X1. Okay. Then let x1 as is. Then if you find x2, then we'll get minus 0 into 1. Obviously, we'll get 0. Okay. If we choose any value of x1, then still we get x2 0 only. Okay. So we start usually from 1. So the required eigenvector we can see x1 is equal to 1 and x is equal to 0. Yeah. Yeah. Pardon? Yes, but when you find any number of eigenvectors, so obviously you will find like multiple of the original. You know, if we take x is equal to 2, x1 is equal to 2, so obviously you'll get 2 0, and then we take 2, and obviously you'll get 1 0 again. You can take any value of x1, then still get the same result. Okay, and obviously you will get this number that is multiple of 1 outside of that. Even if you will not get x2 is equal to 0, for example, if you have a relation like x2 is equal to 3x, okay, and you are taking any value like you are taking x1 is equal to 2 3, or then x2 you will get 3 into 2, obviously 6. Then you will get you write this back 2 or 6. So finally you need to write this 1 and 3. Okay, so when or if you have or anything else, then obviously you will get in the x2, and that multiple of 1 you will find here outside of that as a scalar. My point? Yes, exactly. Then only vector we will find only. Okay, as you are because no, no. If we take any value, okay, you are taking 3, for example, this one. So obvious 3 is like we can write this x1, you know very well. This is very simple. Obviously, final eigenvector you will form same way. Okay, same fine. Still, you have non-zero. If you are like non-zero value, or either you will if have here. Still in vector form, you will get the same value for any. Okay, yeah, this is true for all. So we usually start, okay, by taking when we have any relation like if you have x1 is equal to 2x2 or anything, any relation between coefficient of x1 and x2, then we'll usually start from 1. If either you start from any other number, you will get outside of that vector as a scalar. Okay.
And can you explain to me how to tell the first sum and the cosine?
Uh, Actually, explain you. So, can you give me some more time because we have very less time. I need to explain you. Means geometrical representation and all many things. Okay.
Ma'am, and the required in page 2 in the photo that you sent me. You E2.
So I'm asking. Okay, I'm asking you. Do you remember like vector representation in Cartesian plane or in 3D plane? 3D.
The 2D I know, 3D I don't know how to draw.
Okay, okay. That is why I'm saying that I'll explain representation factors. That is why means then how can we find and how campaign? That is why something.
Message on the group. I mean,
Do you remember vector addition? Doing that according to vector addition.
okay.
Okay.
Vector addition, shouldn't it end up at
See, when we vectors, okay, then we find as resultant, okay, if we this one even e2, then obviously we'll get in this way, not like this. We have like this and this, and don't we get this way, okay?
okay?
Yeah, that is.
With E1 plus E2 and the origin. But in your sketch, you've given E1, E2, and plus E2. And
E1 plus E2 also, see,
yes, sir.
yeah.
Ma'am, we'll do it tomorrow.
So that is why I have sketch according to that, okay?
Okay.
The unit square like this. Obviously, we join these means or mean origin of vectors. Or either take I mean this. Do you or not? Okay, so the geometrical representation of vector from basic to advanced. Okay, first then you will get it easily. Okay, sure.